So welcome to multivariable calculus. This is lecture 29, I think. And so what I want to do today is I want to talk a little bit more about multivariable Taylor series, talk a little bit about convergence of Taylor series, and applications to maxima and minima. I also want to say a few words because on Friday we're going to have our trip to the library. I am still talking to them as to exactly where we're going to meet them. If you need to leave a few minutes early, that's not a problem. I want to just do a little bit of prep work here for when we get to the library. So how many people have read the ancient Greek masters? Okay, this is a liberal arts college. There should be at least a few hands going up, right? They believed, or at least a lot of them believed, that the most perfect motion was circular motion, and all motion is circular. So when you're trying to understand the orbits of the planets, they were trying to have the planets move in circular orbits, either about the Earth or about the sun. The problem is if you actually look at the data, it's not circular. So one of the solutions is if you can only do circular motion, maybe you have a big circle that goes around the sun, and then maybe there's a smaller circle that's turning around the circle. And that gives you a wider class of shapes you can do. But it doesn't give you enough to describe the orbit of the planets. So what could you do next?
The other sort of orbits for the gravitational pull of other things.
No, this is well before gravitational pull and whatnot. So we have a circle, and then we have a circle turning on a circle. What could we do if that's not enough freedom? Add another circle turning on circle. This goes back to some of the theories that the Earth is resting on a giant turtle. And what's that turtle resting on? An even bigger turtle. Like, you have this infinite chain of turtles going down. And so what you can do is you can start adding more and more circles. And depending on how many circles you add or not, it's amazing the types of shapes you can get. You should think of this as philosophically very similar to what we're doing with Taylor series. By adding more and more terms, we're increasing the complexity of what we can look at. And the hope is that things converge at the end of the day. And so we can start asking, what will things look like if we do circles on circles on circles? So let me shift to a Mathematica notebook. Find it. It's actually frustrating. There was one window that it wasn't displaying. So I had to click the extra window saying show all windows. And that one window that wasn't showing was the Mathematica window. It's like, you can't just show that rather than, anyways. So here is just some parametric plots. And so again, Mathematica has a lot of wonderful features that this is the 21st century, you can take advantage of. So here is plotting circle cosine t, sine t, so my x of t, my y of t. And it gives me a nice plot in two-dimensional space. What I'm doing here now is I'm just plotting it slowly. And so as time passes, you can see the path that the object takes up. So it's cosine t, sine of t. Okay. All right, let's do something a little bit more interesting. Let's do some three-dimensional motion. So what I'm going to do is I'm going to take the same curve as before, cosine t, sine of t. But now for the third component, the z component, I'm going to just have it be t over 20. So it's just going to be like a spring. And if you look at it straight down, it's going to still look like it's moving in a circle. But if we look at it from the side, we can see it spinning around. So I can just play, and you can see the path moving upward. Okay. Let's try to do some more interesting shapes now. And so here, the blue curve is fixed. I'm always going to plot a circle of radius 1 centered at the origin. So that's my cosine t, sine of t. The next I have is cosine t plus r cosine ts, sine t plus r sine ts. So if s is fixed to be 1, there's no change. And then if I change the value of r, that's basically drawing another circle. And so what I can do here is, this is the special case when s is 0. So when s is 0, cosine of 0 is 1, sine of 0 is 0. So it's basically just adding r, it's just shifting everything over r units. And that's why in this case, the orange is just the same as the blue circle, just shifted a little bit to the right. And here my value of R is going to be, what is that, about 0.38. And as I change the value here, all I'm doing is I'm just changing how much I'm shifting it over. Okay. I can now increase the value of S. And depending on what I choose for S, I can get some very interesting behavior. If I choose S to be an integer, if I choose S to be 1.5, then when I do something like that now, it's going to cycle back every so many S. I'm going to return to where I started. As I get smaller and smaller and smaller, you can see it's going to approximate the original. So I think the last one was a little bit better. Okay, so here is my last one. So again, it's the same one as before, and I've just chosen some interesting values. So here I'm choosing R to be 0.02. What would happen as R gets smaller and smaller and smaller? What will the orange curve, yellow curve, gold curve, whatever you want to call it, what will that converge to as R gets smaller and smaller and smaller? Circle. Yeah, it'll converge to the circle. So if I go to 0.02, and the reason it's putting things in red is because I said I only want R to go down to 0.2, and this is just giving me a warning. I'm actually making R smaller than I said I would look at. Does that look like a circle to you? Or does it look just a little bit off? A little bit off. If you remember your quantum mechanics, this should look a little bit like some of those things, because I've got a nice integer here, 0.02, some integer number of wavelengths. If I make it a little bit larger, 0.05, you can see it moving out a little bit. And it still seems close to circular motion, but you can start to see the deviations and the fluctuations. If I make this even larger now, I start getting more interesting shapes. And now at some critical point, so maybe I should actually allow this to be a little bit smaller. And so as I increase this, so over here, right here is when it starts to now have this looping motion where it goes backwards. And so we'll talk a little bit about this on Friday, the retrograde movement of Mars. Whereas looking in the heavens, all of a sudden it looks like Mars stops, turns around, and then comes back. It's still circular motion, but because of the circles on circles, I can actually mathematically describe behavior like that. As I keep increasing, you eventually reach the point. Yeah. And I actually think that this is a lot better than most modern math. Because there's some real mathematics going on behind this. This is nice periodic motion. And I can now have my particle just traveling. Now, why do you think it's like that? Basically, mathematics is saying, please slow down, don't make me compute all that. And then when you give it a moment to just rest and catch up, then everything is fine. But just having Mathematica trying to compute all this in real time, it's a little bit hard for it. And it looks like some kind of statically mind-controlled message that I'm sending you. The cycler is mother, the cycler is father. And then all of a sudden it just stabilizes. So we'll talk a little bit about this, but what I hope you can see from this is a really simple modification. This is, 2 circles essentially. Not quite, I've got, 3 variables. Let's say I've got on the order of 3 variables that I'm playing with. I can get a lot of shapes. Now, fundamentally, we do not have circles on circles on circles. We do not have turtles on turtles on turtles. But you can often describe things extremely well by doing stuff like this. And it's just interesting to see how far can you go. Okay. So let's now shift back to the main lecture proper. So we have the multivariable Taylor series, we have the convergence of Taylor series, and we have applications to max and minimum. All right, so we talked a little bit last time about what the multivariable Taylor series should look like. And so if I have some function of, say, x1 through xn, the Taylor series expansion would be first, I'm going to do things all at the point 0. If it was at the point a1, a2, an, we would just replace like that. Then the next piece, the first order piece, not sure why it's shifted, but sure, why not, is the gradient of f dotted with x1 through xn. And then the next piece would be 1/2 x1 xn, then the Hessian matrix, and then as a column vector x1 to xn, and then just us getting worse and worse and worse, trying to write things down. And we talked about this is a very natural thing, and it's set up so that if I take partial derivatives, if I look at the second order Taylor series expansion, all the partial derivatives up to second order evaluated at the origin equal the corresponding partial derivatives up to second order of the original function. So what we're essentially doing is exactly what you would expect. Choose the polynomial such that all the derivatives match up to a given order. And the hope is that, at least locally, the first two derivatives give you enough information to really describe what's going on. And so what we want to do is we want to talk a little bit about generalizing the maxima and minima from one variable calculus to several variables. How do we find places where we could have maxima and minima? Well, this is one of the biggest questions we need to solve in the subject. We want to figure out what is the value to optimize things. How do you find the value to optimize? What do you do? If I have a function of several variables, how do I find my candidates for optimizing?
The first is to look at the endpoints.
I look at the boundary. So one is the boundary, and that's Lagrange multipliers. So Lagrange multipliers tells us what to do for the boundary. Okay, and then for the interior points, how do I find my candidates for maximum and minimum? I look at the gradient. And what should be true about the gradient to be yes? It should be equal to 0. 0 the number, or 0 the vector? 0 the vector, because the gradient is a vector with different components. The gradient, gradient of f is df dx1 ... df dxn. So the notation is sometimes a little bit annoying. We're taking the derivative with respect to x1, but we're calling the point we're evaluating it at x1 through xn. This is why we sometimes expand about the point a1 through an, just so we have a different letter for where we are and where we're moving. Okay. So we already know that if we want to have a chance of having an internal max or minimum, we have to have the gradient vanish at the point. And what this is basically saying over here is this gradient is 0, so that no matter what direction I choose to move, the contribution is 0. So all the directional derivatives vanish. Okay. And now if we want to find out if we have a maximum or minimum, this is where the linear algebra comes into play. Is that we now start looking at the second order piece over here. And remember, in calculus, if I give you the curve, y equals x squared, or y equals negative x squared, then here f prime of x is 2x, f double prime of x is 2. This is a minimum. F prime of x is negative x, f double prime of x, it's negative 2x. F double prime of x is negative 2. This is a maximum. So this is the standard second derivative test from calculus. If the second derivative is positive, it's a minimum. If the second derivative is negative, it's a maximum. It turns out there is a generalization of this in several variables. And again, part of this is making a pitch for linear algebra. Right? I was at my daughter's gymnastics practice, so I was not at the social last night, but there are some times in your life where it's pretty clear what to do next. We talked about how, well, okay, after Calc 1, Calc 2, that's a very natural next thing. After Calc 2, Calc 3, but you could do linear algebra before, or you could even do the two of them simultaneously. After Calc 3, the next math class to really take, if you haven't done so, is linear algebra. If I had to describe linear algebra in one sentence, I would be upset. But if I had to, I would probably say it's about choosing the right coordinate system for the problem you're doing. And depending on what problem you have, different coordinate systems are better. If you answer this with a specific long answer, you will fail this class. As a Bostonian, I hate New York, but in fairness, I have to tip my hat, and I know I've probably said this before in this class, to part of New York about something.
The tap water.
Not the tap water. I'm from Boston. I love that dirty water.
The coordinate grid.
The coordinate grid, where? Which part of New York?
Lower Manhattan.
Yeah, Manhattan, yes. So Manhattan has a beautiful coordinate system. It has the north-south, which are the avenues, has the east-west, which are the streets. If you are in Manhattan, you should orient your coordinate axes along the grid. If you don't, you're an idiot. You know, it's a natural way to describe things. So in linear algebra, it's all about choosing the right coordinate axes. If I give you an ellipse oriented along the coordinate axes, we know how to study this. You know, the equation of the ellipse is x over a squared plus y over b squared equals 1. This is the conic sections that we all forget. We will talk a little bit about ellipses and hyperbolas and all that jazz when we hit the library. What if I give you instead, you know, here's my nice coordinate axes, here's x, here's y. But imagine my ellipse is oriented like this. What you say at this point is, screw the coordinate axes you've given me. I am going to just lean back 45 degrees or whatever. And I'm going to choose these as my coordinate axes. We've already seen a little bit like this when we've done, you know, the change of variables. You know, for certain problems, you know, you should never integrate a sphere in Cartesian coordinates. This is criminal. What coordinate should you use if you have a spherical integral? Spherical, right? And geometrically, what does a sphere look like in spherical coordinates? It's a cube. No. A box. Box. It's a technical term, right? So you know, the sphere would look like a box. We love integrating over boxes. I have my theta, my phi, my r. Well, actually, I guess my rho. So if I do things in the UV system, then I've got u over a squared plus v over b squared equals 1. And then I convert u to a function of x and y and v to a function of x and y. And it turns out that by introducing matrices, what you can do is you can diagonalize a lot of matrices and try to understand what's going on. And so without going into too much, so q of theta is cosine theta. So take me a second. Give me just 1 second. So the physicists and the mathematicians have at times slightly different notation yet again. Are you rotating the coordinate axes in the universe, or are you rotating the point where you are? And so this is going to be a nice rotation. So let's see what this matrix does to some vectors. So if I take q of theta and the vector 1, 0, this is going to be cosine theta minus sine theta, cosine theta, acting on 1, 0. This is going to just be cosine theta times 1 plus 0 times sine theta. That's just cosine theta. Because the way you multiply a matrix and a vector is you do the first row of the matrix dotted with the first column. So it's cosine theta times 1 minus sine theta times 0. And now if I want to do the, that's it for the first row. So now I do the second row dotted with, so it's going to be sine theta times 1 times cosine theta. Does everybody understand how we multiply matrices? If not, I'm happy to just write more details. You should hopefully have seen this with algebra 2, but I want to just give you a little bit of a leg up in case you're going on to linear algebra. I could also have this matrix acting on, oops. Q of theta times 0, 1, cosine theta minus sine theta, cosine theta on 0, 1. So what would I get now if I put in 0, 1?
Negative sine theta, cosine theta.
Negative sine theta, cosine theta. Okay. Okay, so now let's think about what happened. So I started off, here's my coordinate system. Here is the vector 1, 0, and it gets rotated to the vector cosine theta, sine theta. So it's still going to be 1 unit from the origin. It's just now rotated theta. Okay. Similarly, if I look at the vector 0, 1, the start the shear was right where I was writing. If I go here, that's to 0, 1. If you do your trig, it turns out that this is also rotated by theta radians. And so the effect of this matrix is to just rotate by theta radians. So the whole point, if I want to go from maybe XY space to UV space, I can use a rotation matrix and rotate my points. I don't want to go into all the details. I'm hoping that this is enough details for you to see that I can actually take my matrix. And a matrix, there's a lot of different ways of thinking about it. Has everybody seen a matrix at some point in high school? Where you often write it down in terms of solving a system of equations, and you can have that, and you can have that fill in the matrix. You can also view a matrix as we're doing today as it's an operator. It takes a vector as an input and gives you a new vector. Depending on how you write your vector down, the components of the matrix will look different. Whenever you write a matrix down, you always have to choose coordinate systems. And so the whole point is that if we choose a better coordinate system, the matrix is going to look much nicer. So if we choose the UV coordinate system, then we just have a standard ellipse. And so what we want to then do is we can convert from the UV coordinate system by a rotation matrix to the XY system. And so it turns out that many matrices can be diagonalized. And so the key result that you get is that if A is real symmetric, there is an invertible rotation matrix Q such that Q transpose AQ equals D, which is a diagonal matrix. Or A equals Q, D, Q transpose. That I can write any matrix as a diagonal matrix. Do we know any examples of a matrix from this class that are real symmetric? That means the stuff above the diagonal equals the stuff below. So where have we seen in this unit matrices that are real symmetric? So what have we been doing for the last day or two? We've been looking at what? Doing Taylor series. So where do we see a matrix when we do Taylor series in several variables? The Hessian. The Hessian is real symmetric. This is the equality of second derivatives. D squared f dx dy is d squared f dy dx. That's a real symmetric matrix. First take A equals H of that, the Hessian. And the reason this is so useful is now if I look at 1/2, say, x vector h of f times x, this is the same as 1/2, our x vector. H is going to be, so I've got things the wrong way. Sorry. So I guess it doesn't really matter. The way I'm writing things, I want my transpose on the other side. So I'm going to just flip where my transposes are. It doesn't make much of a difference. So I want to do it this way. So Q transpose D, Q X. So this is just 1/2 the vector QX transpose D QX. Okay, well, if I have a diagonal matrix, it's very easy to understand this. So if QX equals B, the above is just the sum, K goes from 1 to N, of 1/2 the kth element of the diagonal times the square of the kth element. So if all dk are greater than 0, we have a min. If all dk are less than 0, we have a max. If mixed, it's a saddle point. So I'm not going to go into more details on this. I'm not going to have you responsible for this on the test. I just want you to be aware of the existence of arguments like this and why linear algebra will now come in useful. Is that locally, we are essentially replacing our function with the value at that one point. Well, that approximation is not so great. That's basically saying nothing ever changes. Who here are my physics students? Okay, are you ever going to take a class called thermostatics?
I hope not.
So what would happen in thermostatics?
It's based on.
No, thermostatics. This is a new class that I've created. Nothing, right? Thermostatics, everything is the same. Nothing changes over time. What is the class you take? Thermodynamics, things change over time. So if we just approximate our function with its value at the origin, nothing happens. So the simplest thing we can do is say, okay, we'll take that as our start, and then we'll do the generalized, tangent line. We'll do the tangent hyperplane. And that's just using the gradient. And then a better approximation is to use the best fit parabola. And then this becomes the several dimensions, and this is where you get the Hessian. And so it turns out we can generalize the second derivative test and get a sense of what's going on near the key point. Okay. So the next question I want to talk about is convergence. So the video you watched, I believe, talked about the birthday problem and some really nice applications of Taylor series to take some very hard calculations and say, rather than doing this painful sum, let's approximate it. It does actually a fairly good job. So the question is, how good of a job does the Taylor series do? I want to know if I need a certain level of agreement, how many terms do I need to take before this is acceptable? And so what we can do is we can say, my nth degree Taylor series is going to be f of 0 plus f prime of 0x plus f double prime of 0 over 2 factorial x squared, all the way to the nth derivative at 0 over big N factorial x to the n. And I could study the error as a function of x is going to be f of x minus the nth Taylor series of x. And I might want to see how large is that? What can I say about this? Well, when x equals 0, I know there's no error. So I want to try to figure out what is the error overall. Okay. So the first thing is, well, let's just naively plug away and see what happens. So this would be f of x minus f of 0 minus, and then I'm going to have f prime of 0x plus f double prime of 0 over 2 factorial x squared plus dot 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 plus the nth derivative at 0 over n factorial x to the n. Anybody have any thoughts about how we might approximate f of x minus f of 0? We do have a theorem that can let us understand f of x minus f of 0. Yes.
The function minus the initial condition.
I'm sorry?
The function minus the initial condition.
Yeah, but where have we seen an expression like that before? The mean value theorem. Normally we see divided by x minus 0. So this over here, by the mean value theorem, is just going to be f prime at some point c, I'll call it c0, times x minus 0. Minus f prime of 0 times x, minus f double prime of 0 over 2 factorial x squared plus dot dot dot. So I just moved the f prime of 0 x over. Oh, how can I approximate that? How can I approximate this? This is f prime of c naught minus f prime of 0 times x. Let me factor this a little bit. This would just be f prime of c0 minus f prime of 0 times x minus f double prime of 0 over 2 factorial x squared plus dot dot dot. How can I approximate f prime of c naught minus f prime of 0? Mean value theorem again, right? So just use the mean value theorem again. And then this will become f double prime at some point, let's call it c1 times c naught minus 0 times x minus f double prime of 0 over 2 factorial x squared plus dot dot dot. So unfortunately, at this point, now we're out of luck, because now I can't combine things nicely. I was able to do it twice. And so if I only want to look at something at this level, okay, but this is not going to continue. It's okay every now and then to see an argument that doesn't work. To say, what's a natural thing to try? Well, I see an f of x minus f of 0. I should be thinking mean value theorem. Okay. So this is the problem is, when you have difficult algebra, it is not always clear what the best way is going forward. Sometimes if you look at things, you can be distracted. Sometimes I just have like a blast helmet on, so you can't see anything. And you have to just try to figure out what are things I could use. Because if you see certain things, they're going to, well, I know f of x minus f of 0. That's a mean value thing. Let me try to use that. And if I start going down that route, I'm going to get stuck. And I get stuck to this point where I can't do anything further because I can no longer combine them. I was able to do the mean value theorem twice. So that looks promising. But unfortunately, after the second time, I just can't go further. So let's over here. So let's try again. So here again is what I have. I have f of x minus t and f of x, that's my error. I liked the mean value theorem. It was doing a nice job, but I could only do it twice and then I ran into trouble. I don't want to give up on the mean value theorem, but there might be a better way of doing the algebra. And again, so much of math is trying to find what is a good way of looking at the algebra, how can I use it? What I'm going to show you is not the best bound possible. It's going to give you the right error in terms of x, but it's not going to give you the best constant. but it's an easier proof. So I like this proof. All right. What do we know about the Taylor series in F? We know that they have the same value at 0. They have the same derivative at 0. They have the same second derivative at 0, all the way up to their nth derivative is the same. Okay. So let's construct a new function. Let's let g of x, which is essentially just our error function, be f of x minus Tn f of x. What is g of 0 equal to? 0. What's g prime of 0 equal to? Zero. All the way up to the nth derivative at 0 is 0. So one way to view my error is equal to g of x, right? Two of the greatest things you can do as a mathematician is you can add 0 or you can multiply by 1. Can anybody think of a good 0 I could add to g of x? So it's on the board. Yes. I could add g of 0. Or technically subtract g of 0. So we did nothing. But we did nothing in a very good way. Now, what can we use to study g of x minus g of 0? Now we can use the mean value theorem. And when we use the mean value theorem, this is going to be g prime, bless you, at some point I'll call it C0 times x minus 0. So this is just g prime of C0 times x. I want to add 0. How can I add 0 to this? Well, if I add g of 0, that's going to be bad because I'll have a g of 0 and a g prime of 0. They're not going to line up. Almost. G prime of 0 times x. So this is just going to be g prime of C0 minus g prime of 0 times x. So notice, unlike the last one, I'm now aligning everything every single time to make the mean value theorem easy. What's g prime of C0 minus g prime of 0? How do I estimate that? So what would I use to estimate g prime of C0 minus g prime of 0? The mean value theorem, right? So by the mean value theorem, this is going to be g double prime at some point C1 times C0 minus 0 times x. And so here, C0 is between 0 and x. C1 is between 0 and C0. So now I can write this as g double prime of C1. What do I do? So how would I add 0?
Subtract g double prime with 0 times.
Yep. And now do you see that every single time I use the mean value theorem? Before, I had trouble when I got to the second derivative. When I was looking over here, okay, I had the f double prime of C1 times crap minus the f double prime over 0. But I have an x squared over 2 versus a C0 x. And that was a problem. But here now, I can just keep adding 0. And so what will I get when I now use the mean value theorem yet again? This would just become g triple prime at C2 times C1, C0 times x. And now we would just subtract g triple prime at 0 and just allow the rinse repeat. So as we continue, we would get that the error at x would eventually be the n plus first derivative at some point Cn times, and now if you look over here, we had the third derivative at C2, and then it was C1, C0 times x. So it's the nth derivative, n plus first derivative at Cn would be times Cn minus 1, Cn minus 2, C1, C0 times x. So the absolute value of the error at x would actually be less than equal to Gn plus 1 of Cn, and we'll take the maximum over Cn less than equal to x times x to the n plus x to the n plus 1. So let's think about why that's true. The number of factors we have here is n plus 1. Because I start my counting at C0, so from C0 to Cn minus 1, that's n factors, and I have one more for the x. So I have n plus 1 factors. And then I'm replacing the n plus first derivative with the maximum value over all choices that are at most x in absolute value. So let me just write this up. So this is going to be the maximum over C. Okay. Maximum not sure why it's not letting me write all of that. Okay. All right, so this would be less than equal to the maximum over Cn less than equal to x, the n plus first derivative at x. I'm sorry, no, Cn times x to the n plus 1. All right. So this is a nice formula for the error. So if x is of size 1/10 and n equals 5, this would be of size 1/10 to the 6th for the error. The problem, of course, is, well, what if the n plus first derivative is really large? So if you have some bounds on the size of the n plus first derivative, then this becomes really good. The difference between this and the optimal result is, with a little bit more work, I believe there's a factor of n factorial you can have in the denominator. Okay, I wouldn't mind having a 10 factorial in the denominator. That's not so bad. But what's really important is seeing how it goes with x. The other thing is, if you give the language, this is a no shit Sherlock moment. I'm looking at the first big N derivatives, and my error is of size n plus 1. Okay, yeah, that kind of makes sense. I'm truncating my polynomial and taking degree n. The error should be something of degree n plus 1. So this is just rigorously proving that if your function is n plus 1 times differentiable, so differentiable once more than the number of derivatives you're looking at, you can use that to get a decent error estimate. And we can now use this to approximate how close are we to our function. How many of you have ever been on an elevator? What is the first thing you should do when you get on an elevator? Nope. Check the weight limit, right? Is this a safe elevator for me to be on? How do you think they determine? Do they just keep putting on, do they have two elevators that are identical, keep putting people in and see when the elevator crashes? What do they do? Right, so which do you want to do? Do you want to underestimate or overestimate the safe limit?
You want to say the one is a lot lower.
Correct. You want to actually have a little bit of flexibility. Because if you go over by just a little bit, there is a huge cost to being a little bit over and having the thing crash and everybody dying. And you weigh that versus underestimating. And if you say, well, you can only take 2,000 pounds, but if you really take 2,500, or maybe you have the elevator not having as full of a capacity as possible sometimes, especially if it's a cargo elevator. So that means you have to use more trips, more energy and whatnot. But the probability of it breaking, if that is sizable and the harm of it breaking is so bad, you would much rather underestimate and be safe than overestimate and have it break on those few days. So when you are making a lot of things, and a lot of science fiction shows, Scotty is famous for this, when he talks to Joe to the Collision, you always have a little bit of a fudge factor, a little safety margin, and when you're writing down the books as to just what can things be done. So that you can go a little bit above. The question is, how much above can you go safely? But you want to be able to make some rough estimate as to what is going on. These calculations are extremely important. And again, what I'm trying to do in this class is just give you a sense of general mathematical techniques that you can use in a lot of things in the future. Here, I'm just trying to get a ballpark sense of how close are we. Not surprisingly, the smaller x's, the closer we are to the point we're expanding by, the better we should be doing. And that is going to be for two reasons. One is the fact that x to the n plus 1 will be smaller if x is smaller. And two, we have this maximum, and that maximum is going to be over a smaller window. So if you take a maximum over a smaller window, it can't get larger. So it's a really important question to try to figure out just how close are you and how much you can trust things. All right, so I think this is a good amount of Taylor series for the course. We've seen how to compute them. We've seen connections in linear algebra, so that if you do take a class in linear algebra, you might see some of these theorems about how do you tell if you have maximum or minimum, and begin to see why we might care about diagonalizing matrices. And the idea is we want to study things in as simple of a manner as possible. Align yourself, if the ellipse is not aligned with the coordinate axes, change the order of the coordinate axes. And then the last thing was, how do you do algebra? If you know something, I have a hammer, all I see is nails. I love the mean value theorem. It's one of my favorite theorems. It's the poor mathematician's Taylor series. I mean, that's really what it's doing. The mean value theorem really is, f of b is f of a plus f prime at some point c times b minus a. So it's almost where you started plus your instantaneous speed at that time times the distance. The reason it's not is because you're evaluating it at some intermediate point. And the mean value theorem just says there's some point that works. We don't know what it is, but there's some point. The Taylor series says we're going to just expand about the point that we care about. And then all that we did is just trying to magnify and figure out what is the error from there. But when we did the proof, the most natural thing was, well, let's group things together. And this is why I really wanted to do a proof that would not work out well. Because when you do this, you see you get stuck. And it's just so easy to fall down the path of just doing algebra, algebra, algebra. And then it's step back and think, we're using the mean value theorem. What do I want for the mean value theorem? I want to have f of b minus f of a. Wouldn't it be nice if f of a and all of its derivatives were all 0? Oh, I have a function like that. If I just look at this difference. So the problem was we tried to view this initially as f of x minus t and we should have really viewed it as itself minus 0. That's what we were really doing, is that there was really just subtracting 0 the whole time. And so we were just grouping things the wrong way. So much of life is just grouping things the wrong way. All right, this is a good place to stop. I will send you details later when I find out exactly where we're meeting for the library. Have a great day all.